Okay, hi all, welcome back. Today we want to look at the idea of a different type of sequence. So far we've only been looking at linear sequences, and today we want to move on to a quadratic sequence. And we should be used to this term quadratic because we've seen it in a few different contexts before. We've seen it when we talked about quadratic equations, and we've seen it with quadratic functions. And in fact we had linear equations and linear expressions as well, and linear functions when we were talking about functions. So it's the same idea, and it's the same way you'd identify a quadratic sequence as you'd recognize a quadratic equation or a quadratic expression, or indeed a quadratic function. So first of all, if we look at, if we had term n of a linear sequence, let's see what it looks like. These are three different linear sequences. Tn equal to 3n plus 1, Tn equal to 5n, Tn equal to 1 minus 2n. So you might notice what they have in common, and what allows you to say straight away that those are linear sequences is that they all have to have an n part on this side, okay? And the n part, the highest power has to be the power of 1. So we can't have an n squared in here, or it'll no longer be linear. We can't have an n cubed, an n to the power of 4. The highest power has to be n to the power of 1. We don't have to have a constant. In this one we see we've no plus 1 or plus 3, but we must have the n. We don't have to have a coefficient. For instance, this is also, that's also a linear sequence there. Okay, so some ideas of quadratic sequences. So you should be able to spot a quadratic sequence immediately if you saw it written down, if you saw the general term rather of it written down, or term n. So here we see a few examples. Tn equal to n squared, Tn equal to n squared plus 1, Tn equal to 2n squared minus 2n, term n equal to n squared plus 2n minus 1. So what do they all have in common again? They've all got an n squared part in it. Okay, a quadratic sequence has to have an n squared part, and it can't have anything higher than n to the power 2 in it. In other words, it can't have an n cubed in there as well, or else it would no longer be quadratic, it would be cubic. So it has to have an n squared, it can't have an n to the power of anything higher than 2. Then it can also have an n part in it, but it doesn't have to have an n part. It can also have a constant in it, but it doesn't have to have a constant in it, as we see here. Or it can have all three things, an n squared, an n part, and a constant. So quadratic we recognize really by the n to the power of 2 somewhere inside in it. Okay, so for our notes, the first thing we might say about quadratic sequences is that term n is, term n is of the form Tn equal to an squared plus bn plus c. Now, I'll explain that again. Let's have a look at it in the context of these quadratic sequences we have here. So if I write, take one of them down here, this one here, the last one I think is easiest to see. Tn equal to n squared plus 2n minus 1. So that is in the form Tn equal to an squared plus bn plus c, because we can see the a in this case is equal to 1, isn't it? A is equal to 1 because this is the same as 1n squared. The b part is equal to a plus 2, isn't it? It's because that's plus 2n. And the c part is equal to minus 1. Now, this is easily recognizable as being in this form where a, b, and c are some number that goes in front of the, as a coefficient for the first two parts and as a constant for the third part. But let's look at ones that aren't as obvious, like for instance this one. Tn equal to 2n squared minus 2n. So in this one, the a part is obviously 2, that's the an squared. The b part is minus 2, so plus bn, our b then is minus 2. And our c part, well, we can write this as plus 0, can't we? I mean, adding 0 to something doesn't change it at all. So our c part is equal to 0. So all quadratics can be written in this form, even if we don't see them like that initially. So for instance, look at this one, which doesn't seem to be at all like that. Tn is equal to n squared. Well, again, if we write it as plus 0n plus 0, we can see that the a part is equal to 1, because this is the same as 1n squared. The b part is equal to 0, and the c part is equal to 0, because adding 0 n's onto something doesn't change it, it's just adding nothing. And adding 0 doesn't change it, it's just adding nothing. So all quadratics can be written in that form. That's the first thing to learn. Okay, the next part we need to understand about this is, that if we were to try and recognize a quadratic sequence given term n, we'd be able to recognize it because of the n squared part. But sometimes we're not given the quadratic sequence in terms of the general term. Sometimes we're given the actual numbers, the actual terms in the sequence. Well, when we are given the terms, we recognize it as quadratic by knowing that in a quadratic sequence, the second difference is constant. The second difference is constant. So let's look at how that works from an example. Imagine you get this 1, 4, 9, 16, 25, 36. Okay, so that is a quadratic. I can tell you just by looking at it that term n is equal to n squared, because term 1 is 1 squared, term 2 is 2 squared, term 3 is 3 squared. But if we didn't know that and we just had these numbers and we didn't know and we wanted to check if it was quadratic, what we do is we test first of all to see if it's linear. So we look at the first difference and we see 1 to 4 is going up by 3, 4 to 9 is going up by 5, 9 to 16 is going up by 7, going up by 9, and going up by 11. Definitely not linear anyway. That's the first difference. So definitely not linear. So this is what we call the second difference. It's, if you like, it's the difference between the first differences. So we look at here, 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 and here. And we notice 3 going up to 5 is going up by 2. 5 to 7, 2. 7 to 9, 2. 9 to 11, 2. We can say definitely that the second difference in this case is constant, isn't it? The second difference is always 2. So in that case, this is definitely a quadratic, because in quadratic sequences, the second difference is always constant. Okay, so all we want to do today is we want to find out, what does a quadratic sequence look like? It looks something like this. How do we recognize, or how do we show that a quadratic sequence is quadratic? Well, we find the second difference and we show that it's constant. Okay, and the last thing we want to do, and this is the longest part, we want to work out how do we find term n of a quadratic sequence, because there isn't a formula for it in your log tables. I got to warn you now that in your log tables, I've told you already, you don't use this until leaving cert. This is not a formula for quadratic sequences. Geometric sequences are not the same thing as quadratic sequences, so this will not work when it comes to quadratics, and in fact you will not use this at junior cert. Okay, so the only one we're going to be using is that one up there, the first one we used for linears. So we have another way of finding term n. There are several ways, but we'll go through one today of finding term n of a quadratic sequence. So I think the best way to do that is to use an example. So we'll say find term n of the following sequence. Okay. And the sequence we're going to go with is this: 3, 6, 11, 18, 27. Okay, now I haven't told you whether it's linear or quadratic, so we must first decide what type of sequence it is. So we look at the differences. 3 to 6, that's going up by 3. 6 to 11, it's going up by 5. 11 to 18, it's going up by 7. 18 to 27, it's going up by 9. So definitely not linear. That's all we can say at this stage. Now, if it turned out the second difference wasn't constant, then all we could say is it's not linear and it's not quadratic. At that stage, that's all we could do. But in this case, luckily enough, when we check the second difference, that's going up by 2, going up by 2, 5 up to 7 is up by 2, 7 up to 9 is up by 2. We can see that the second difference is constant, therefore it is a quadratic. Okay, so how do we find term n of a quadratic sequence? Here's what we do. First of all, we know that every quadratic sequence is in this form, or can be written in this form. an squared plus bn plus c. Okay, the next thing, and this is new, the a part, the bit that goes in front of the n squared, the coefficient of n squared, is always equal to half of whatever the common second difference is. So in this case, since the second difference is 2, the a part is equal to 1, half of this, half of 2, which is 1. So we'll just write that down. That's very important. A is equal to half of the second difference. That's vital to figuring out what term n is. So if that's the case, we already have a little bit of the puzzle solved. Our term n for this particular sequence must be half of 2 is 1. If I put in 1 instead of the a here, it's 1n squared plus bn plus c. We must still find the b part and the c part to figure out what term n is. So this is the next step we take. What we do is we take any one of the original terms of the sequence. So these are the differences underneath, but the actual sequence itself, these are the terms in the sequence. So we took any two of these, and I like to just take the lowest ones usually because smaller numbers are easier to deal with. So if we take the 3 first of all, we can say that term 1 is equal to 3. Just by observation, term 1, the first term, is equal to 3. Okay, but we have a way of finding term 1 when we know what the general term is as well. We often use the formula and find what term 1 is. So for instance, I might, if I had this full formula, if I knew what b and c was, I could find term 1 by subbing in 1 instead of the n's. So it would be 1 times 1 to be squared plus b times 1 plus c. Now if I tidy that up, that means term 1 is equal to, well, 1 squared is 1 times 1 is 1. B times 1 is b. Term 1 is equal to 1 plus b plus c. So if I knew what b and c was, and I subbed them in here, then I should get a value of 3 for term 1, shouldn't I? But I don't know what b and c is. But what I do know is that if term 1 is equal to 3, and term 1 is equal to 1 plus b plus c, then 3 must be equal to 1 plus b plus c. They have to be the same thing, don't they, if they're both term 1. So I can, in my next line, I can say that it implies that 1 plus b plus c is equal to 3. And tidying it up a little bit, bringing the 1 over to the other side, it becomes a minus 1. I can say b plus c is equal to 3 minus 1, which is equal to 2. That's using the first term. Now I'm going to do that a second time. With the second term, I'm going to get another equation, linear equation, on 2 variables in terms of b and c. And taking term 2, I know term 2 is equal to 6. I know also, if I use my formula, what I have of it so far, even though it's incomplete, but I know if I try and find term 2 using the formula, it will be 1 times 2 to be squared. I'm subbing in 2 here and subbing in 2 here, plus b times 2 plus c. And tidying that up a little bit, term 2 is equal to, well, 2 squared is 4, times 1 is just 4, plus 2 times b is 2b, plus c. That's a poor b. Much better. And then bring that over here. Well, again, I can say if t2, term 2 is 6, and term 2 is this, well then 6 must be equal to all of this. So if I put it as 4 plus 2b plus c equal to 6, and then tidying it up, bringing the 4 across to the other side, it becomes a minus 4. Then I'm left with 2b plus c on the left and 6 minus 4 is 2 on the right. So what I've got now is two linear equations of two unknowns. I can use my solving simultaneously and find the value of b and c here. When I find b and c, I can just put it in here, and I'll have my term n. So very briefly, I've done this loads of times before. So start with my 2b plus c equal to 2. And underneath it, I'm going to put my other equation, b plus c equal to 2. And because I want the c's to have different signs, I'm going to change all the signs in the bottom. That becomes a minus, this becomes a minus, this becomes a minus. And 2b take b is 1b. C's cancel. 2 take 2 is 0. So straight away I've got b is equal to 0. So what I'm going to do is take one of my formulas again, b plus c, one of my equations, equal to 2. I'm going to sub b equal to 0 into it. 0 plus c equal to 2. Well, that just means that c is equal to 2. So all I'm left to do now really is to sub my value for b and my value for c into this term n equation. So term n is equal to, we already had the 1n squared. Now you don't have to put the 1 in there because 1n squared is the same as n squared. And the next thing is plus 0n, and then c is plus 2. Now, of course, you don't have to write that. You could just say Tn is equal to n squared, 0n can be left out, plus 2, and that's term n for that particular sequence up here. Now, what I would do always is just test out one other. Like we've been using term 1 and term 2. Let's just see if it works for finding term 3, just to make sure that we haven't made a mistake anywhere along the way. So term 3 is equal to, subbing 3 in here. We can already see 3 squared is 9, plus 2 is 11. Okay, so just a quick review for today. What do we do? We introduce quadratic sequences. We know how to recognize them when they're written in this form. When you're given term n, they look like one of these, n squared, 2n squared minus 2. We learned that the second difference in a quadratic is constant. So if you're given the actual terms themselves, you can show or prove or find out that they're quadratic by just checking the second difference to see if it's constant. And then the last thing is we learned how to find term n, or the general term or the nth term of a sequence when they give you the terms in the sequence, when they don't give you the actual formula, if you like, they just give you the terms. Okay. And the very first part of doing that is find the second difference and halving it. So half of 2 is 1, and that gets you the a part in your term n. And then you use simultaneous equations to find the b and the c part.